one of the simplest approximations you can use to use the variational principle to solve the Schrodinger equation. And that method is called the Hartree Fock Approximation. Okay? All right, so just a quick recap. This is our stationary Schrodinger equation for a system of atoms. Okay? We are where we basically have all the kinetic energy terms for the nuclei and electrons and all the electrostatic interactions between the electrons and the nuclei with themselves and the electrons with electrons. Okay. Now, I'm going to first simplify that stationary Schrodinger equation a little bit. Okay. I'm going to use what are called atomic units. So atomic units are basically units where your units of things like the mass and charge and action and the electron constant are actually based on things like the elementary electron charge and the electron rest mass and so on and so forth. Okay. Now, when you use atomic units, what happens is that your Schrodinger equation then simplifies considerably. Okay. So you'll see that this is still the same equation as you see before, but in atomic units. And what you see is that now this is my kinetic energy term for electrons. I no longer have the electron mass because now the electron mass is basically my unit of mass. Okay, so this is just a half. I still have my reduced mass for my nuclei, and my electron charge terms also disappear because my electron charge is my unit of charge. Okay, so we are going to use this simplified equation from now on. Okay, just for simplicity's sake. Okay, don't worry too much about it. This is just to provide you with some theoretical grounding on the Hartree Fock method. You are not actually going to solve any of this by hand. Okay. All right. Now, as I mentioned before, we based on the variational principle, we can judge the quality of the wave function based on how low the energy is, right? Okay. So this is the variational principle, right? So how do we use this? Okay. One simple way is to use what is called a linear combination of atomic orbitals approach. Okay, so this was one of the earliest ways in which the variational principle was used. Okay, so in linear combination of atomic orbitals, what it simply means is that if I'm looking at, for example, a diatomic molecule where I have a bonding between two states. Let's say my hydrogen atom, which is a 1s, and another two hydrogen atoms with 1s orbitals. Okay. What I would do is that to model the molecular orbitals, which is the system of hydrogen as a whole, I'm going to assume that my molecular orbitals are some linear combination of my atomic orbitals of hydrogen. Okay. Now, of course, this is a very reasonable assumption, right? It's quite a natural assumption to make that if you have two hydrogen atoms, individually they have atomic orbitals. When you put them together, your resulting molecular orbital is just some linear combination of your atomic orbitals, right? Now, using this, you can already solve the Schrodinger equation for some simple systems, right? So now, usually when we try to solve the stationary Schrodinger equation, what we first need is to first come up with some trial wave function, right? So usually what we do is that we expand that trial wave function in terms of a series of mathematical functions, and these are what are known as basis sets. Okay, so in the linear combination of atomic orbitals approach, what we are using for our mathematical function here is basically the atomic orbitals themselves. Okay. Well, of course, there is, as you will see later, we are not this is not limited to just atomic orbitals. You can actually use any set of basis function, mathematical functions as your basis functions. Okay. So so for single nucleus, the eigenfunctions are effectively what the hydrogenic atomic orbitals. So for our molecule, basically what we are going to do is that we are going to use the atomic orbitals as our basis set, and this is this basically leads to what is called a linear combination of atomic orbitals. Okay. So now let's see what happens when we plug that into our equation for the energy. Okay. So as you recall, the energy is equals to this integral, the phi of phi h phi, which is phi, where phi is basically my trial wave function, which is this linear combination of mathematical functions that you see here, okay, divided by this normalization term, which is the integral of the square of that square of phi across all of space. Okay. Now, if you do some rearranging, basically what you get is this term over here. Okay, so you have your coefficients ai, aj, and what you have here is basically the integral of your basis function with phi of I with h with psi of j, right? And the bottom just simplifies to just this expression over here, which looks very similar, except that there is no Hamiltonian in the middle. Okay, and this is of course just equals. We can just call this integral h of ij. This is what is known as the resonance integral. Okay, and the bottom, which is basically the integral of the basis functions with each other, we call this the overlap integral, which is S of ij. Okay, so in other words, the energy is just given by this summation over all of ij, ai times aj times the resonance integral h of ij divided by this summation over all of ij, ai aj times the overlap integral S of ij. Okay. Now, so basically, as you recall, what we want to do is to find the minimum energy solution for all my coefficients a of I and a of j, right? That basically gives me my solution to my Schrodinger equation, right? So how do we find the minimum of a function, right? What we do is that we take the derivative of the energy with respect to all of my coefficients a of k, right? So we take the derivative, we set it to 0 for all the coefficients a of k. And what you get is basically this equation over here, which is this is summing over I equals 1 to n, where n is basically your total number of basis functions, ai, h of ki minus e, the overlap integral S of ki equals to 0. Okay, so you can actually verify this for yourself by doing the differentiation. Okay, don't worry too much about it. So if you recall, we basically need to do this for every single k, okay, for every single basis function. And what results is that this equation, you can actually write it out as this matrix equation over here. Okay, so you can see that h11 minus e11 is equals to 0. So this is basically this term over here plus this term over here times a2 and so on and so forth, and that gives you this vector right here. Okay, you can verify for yourself that this matrix multiplication is essentially what this equation is saying. Okay, now to solve this matrix equation, basically what we need is to find the eigenvalues. Okay, and this matrix equation only has a non-trivial solution if the determinant of this is equals to 0, right, from your linear algebra. Okay, so that's basically what we do. We basically set that the determinant of this matrix to 0, and we basically solve for the eigenvalues of the solution. Okay, so the procedure for solving this circular equation is very simple. Essentially, you select a set of n basis functions. Okay, so in the linear combination of atomic orbitals approach, you basically use the atomic orbitals. you determine all n square values of Hij and Sij, which is your resonance and overlap integral. And then you form this circular determinant and determine the n roots of your E of j, okay? And for each E of j, then you plug it back into your equation to find out what your A of I is, okay? And once you do that, you basically have all your coefficients, and with the coefficients, you basically have your solution to your Schrodinger equation, okay? All right. So, so there are some very, in the early days of quantum chemistry, there are some very simple ways in which you can, simple approximations that people have used to solve some of these equations. Okay, so one simple way is to use what is called Hückel theory, okay, where essentially if you think about something like this propylene molecule over here, okay, and you assume that the basis set is formed from the parallel 2c orbitals, which are the orbitals that are perpendicular to the plane of your molecule, okay. So, and you just make some assumptions, like for example, the overlap matrix is just given by delta ij. In other words, you are assuming that there is no overlap at all between any of your neighboring 2p orbitals, okay. And you assume that your diagonal terms, Hii, is just equals to the ionization potential of your methyl radical. And what you then have is this very simple equation over here, which is for Hij for nearest neighbors, you actually obtain it from experiments, and for nearest neighbors, right? And you assume that the value, the resonance integral is actually 0 for neighbors that are further away. Essentially, what you can do is that you can, what you get is basically this very simple expression over here, and you can then solve this equation to get some approximation of your molecular orbitals for your this molecule. Okay, so this is just an example of one of the very simple ways in which people use this use the circular equation. Okay, now. We are actually going to go into something a bit more practical. Okay, so nowadays Hückel theory is very seldom used. Okay, so in order for us to solve that equation, we actually have to rely on one more approximation. Okay, which is what is called the Born-Oppenheimer Approximation. Now, the Born-Oppenheimer Approximation is actually a very simple concept. It's just the Born-Oppenheimer Approximation simply states that the heavier nuclei moves much more slowly than the electrons, right? So in other words, you assume that when your nuclei are in a certain configurations, your electrons would instantaneously just relax to whatever nuclear potential that you have based on the configuration of your electrons, based on the configuration of your nuclei, okay? So what this simply means is that we now can assume that because our nuclei motion is moving much more slowly, we can take the nuclei motion out of the equation. We will just solve what is known as the electronic Schrodinger equation. So for the electronic Schrodinger equation, you basically have your Hamiltonian for your electrons plus the potential that is given by your nucleus coordinates. And all that you worry about is the wave function of your electrons only, okay? So you are not going to worry about the nuclei at all, okay? And what you get, of course, as eigenvalues are basically the energies of your the electronic energy, okay? All right. So for the stationary electronic Schrodinger equation, basically what you have is the energy. Basically just the electron-specific terms, okay? So you have your kinetic energy of your electrons. You have the attraction between your nuclei and your electrons, and the repulsion between electrons and electrons, okay? So let's go back to the original stationary Schrodinger equation. There are two terms which are specific to the nuclei, right? So this term over here, this is basically nuclei kinetic energy, okay? And this last term over here, this is nuclei repulsion. Okay, so these two terms only relate to the nuclei. So when we think about, when we apply the Born-Oppenheimer approximation, we are essentially saying we are not going to care about these two terms. Okay, we are going to treat them separately. And we are only going to care about the other three terms which actually affect the wave function of your electrons. Okay, so this basically gives this equation over here. And what you notice immediately is that the kinetic energy term and the nucleus electron term, they are separable. Okay, now we are going to worry about this last term later. Okay, let's worry about the electron repulsion later. We are just going to think about the kinetic energy term and the nucleus nuclei attraction term. And you can see that this term is separable. In other words, we can separate it into a summation of individual wave functions for each electron. Okay, so we can think of this part as basically a summation of lowercase h of I, where the lowercase of h of I is basically just the sorry, this should be del square, the kinetic energy of the individual electron and the interaction between that electron and all the nuclei. Okay, so this is basically the interaction of the one single electron with all the nuclei, and this is the kinetic energy of that single electron itself. Okay, all right. Now, when we think about the how do we actually use this? Okay, so what we will do is that we are now going to if our electronic Hamiltonian is separable, basically what we can do is that we can treat each of them in terms of a Hartree-Product wave functions, right? So in other words, we now simplify our equation into just lowercase h of I times phi of I equals to epsilon I times phi of I, where this phi of I is basically the eigenfunctions of your one electron Hamiltonian, right? Now, because your overall wave function is separable, basically your because your overall Hamiltonian is separable, your Hartree-Product wave function is just equals to the product of your individual electron wave function, and you can show that basically your total Hamiltonian multiplied by your Hartree-Product wave function is just equals to summation I h of I, the product of each of your one electron wave functions. Okay. In other words, your eigenvalues is basically a summation of all the individual electronic energies of your single electrons. Okay. Now, so now we have one remaining problem, right? So as I mentioned, this part is separable, but this part is not, right? Because this is the interaction of that one electron with every single other electron. You cannot actually separate out this part into a separable function by itself. Okay, so in the Hartree Fock approach, basically what you do is that you use what is called an effective potential approach, right? So to include the electron repulsion, we think of each electron as seeing an effective potential from the other electrons that is not itself. Okay, so for now we are going to denote this effective potential with this V of ij, and this V of ij is just equals to the summation across all the electrons except the electron itself, and we are just integrating the charge density and divided by Rij, okay, which is the this is basically the electrostatic repulsion term from all the other electrons. Okay, so in other words, we are thinking of all the other electrons as basically electron cloud, and we are thinking of the interaction of that of our electron with that mean field. Okay, so with this, by plugging this in, by treating our one electron wave function as this, we now effectively have a separable Hartree-Product equation, we can then use our Hartree Fock approach to solve it. Okay. All right. So what's the procedure for doing a Hartree Fock calculation on a molecule, which is the simplest approach that you can use? So you usually start with some guess for your molecular orbitals. Okay, so you can expand the molecular orbitals using any set of basis functions. You can do it using atomic orbitals. You can also use it do it using some other basis functions. We are going to talk about what are some of those other basis functions that we are going to use. We are going to construct all these one-electron operators. Okay, so this is my one-electron operator. I'm going to solve for my wave function using my separable one-electron Hamiltonians. Okay, and using my new wave function, I'm going to reconstruct my molecular orbitals. Okay, and then I'm going to repeat this whole process. Okay, so in other words, I'm going to keep looping this consistency loop until my wave functions or my energy doesn't change that much. Okay, and that gives me my guess of my wave function. Okay, now once my energy converge, my final energy is then given by my summation of all my E of I. Okay, but you will notice that I actually need to subtract out this term. Okay, think of this equation, right? For every single electron, I am calculating the interaction of that electron with all other electrons, right? So what this means is that I'm actually double counting the interactions. I'm counting the interaction between electron 1 and electron 2, and when I'm calculating the Hamiltonian for my electron 2, I'm also calculating the interaction between electron 1 and electron 2. So I'm doing double counting. So this, if you look at this is basically just a double integral of my charge density of my electron 1 with all the pairs of electrons. So I'm subtracting half of this energy because I've already double counted this energy twice in my summation of h of I. Okay, and this is why that subtraction is needed. Okay, and I've not taken into account a Pauli exclusion principle, right? So what is Pauli exclusion principle? The Pauli exclusion principle simply says that two identical fermions, basically spin half particles, in other words, your electrons, cannot occupy the same quantum state simultaneously, right? So the practical effect of the Pauli exclusion principle is that you cannot have an electron with the same spin occupying the same energy state. Okay, so and what this also means is that your wave function itself has to be antisymmetric, right? So when you actually swap the wave functions, that swapping has to be an antisymmetric function. Okay, so for two electron system, basically what you do is that you construct what is called a Slater determinant. Okay, so your wave function is then given by this Slater determinant, which is 1 over root 2. This wave function for A, and then a spin wave function for A, alpha, and then if you write this out, this determinant, you basically get your Slater determinant wave function. Okay. All right. Now, for many electrons, the Slater determinant then expands correspondingly. For n electrons, you basically have a Slater determinant with n terms. Okay, and this chi k are basically what are known as the spin orbitals. Okay, so that's just one slight complication when we need to deal with that we need to handle to deal with the Pauli exclusion principle, right? All right, so so this is after you take into account the Pauli exclusion principle, what you end up with is basically I would say the most low-level method you can use to solve the Schrodinger equation, which is what is called the Hartree Fock self-consistent field approach. Okay, so this is typically the simplest method that you will encounter in quantum chemistry courses. Okay, so in fact, in some quantum chemistry courses, this would be one of your projects would be to, for example, implement the Hartree Fock solution inside MATLAB, okay, for example, right? So in the Hartree Fock approach, your individual electron operators are now what are called the Fock operators. Okay, you basically again, you still have your kinetic energy term, your nuclei term, and your external potential is now given by what is called your Hartree Fock potential, right? So and this circular equation still looks very similar to the one that I showed you for the Hartree self-consistent field approach. Okay, except that instead of your resonance integral, now you have your Fock integrals, okay? And these Fock integrals are just basically given by this expression over here, where this term basically accounts for your mean field interaction between your electron with the rest of other electrons, including the effect of the Pauli exclusion principle, okay? All right. Now, this is, in a nutshell, how you go about doing using the Hartree Fock self-consistent field approach. Okay, so this is the flow chart. You first start by choosing a basis set. Okay, so right now, for the purposes of this lecture, for now you just think of the basis set as, for example, your atomic orbitals as your initial basis set. You have some initial guess of the molecular geometry, right? So in other words, in every calculation, you usually start with some set of coordinates of your atoms, okay? It usually has to be some reasonable guess, okay? You don't want to be too far away from your equilibrium state. But as long as you have a reasonable guess, that's fine, okay? You then go through this internal loop. This internal loop is basically what is called the electronic self-consistent loop, okay? So you compute all your overlap, 1 electron and 2 electron integrals. You create your initial charge density matrix. You construct and solve that Hartree Fock circular equation that you see here, okay, this one right here. And you then reconstruct your density matrix from your occupied molecular orbitals. And then you ask yourself, well, is my density matrix significantly different from my the density matrix that I obtained in my previous iteration? Okay. Now, if not, or rather, if it is sufficiently different, okay, what I would do is that I'm going to do this electronic self-consistent loop again and again. I'm going to take this new density matrix. I'm going to replace my gas molecular orbitals with my new molecular orbitals, and I just keep looping this until I get a good set of density matrices, okay, or a good set of wave functions, okay. Now, this electronic self-consistent loop only takes care of the electronic convergence, okay. What this means is that given the position of the nuclei, I am optimizing the set of wave functions for that position of nuclei, okay? It doesn't mean that those position of the nuclei is actually the lowest energy configuration for that set of atoms, okay? So basically what you have then is this outer loop, right? This outer loop is what is called the ionic self-consistent loop, right? So in this outer loop, after you have already solved for your electronic convergence, you will basically look at the molecular geometry, and then you are going to calculate the forces on each of the atoms, and then you see whether there's significant forces on any of the atoms, okay? If there are significant forces on any of the atoms, or the energy is not low enough, basically what happens is that you choose the new geometry based on some algorithm that or some approach, okay, and then you just repeat that whole process over and over again, okay. So there is a nested loop here, right? Okay, so there is that ionic self-consistent loop where I'm adjusting the positions of my atoms, and there is this electronic convergence loop where I'm adjusting, I'm trying to find the optimal set of wave functions for a particular set of positions, okay. And of course, after you satisfy both the electronic and ionic convergence, what you end up with is an optimized geometry for your atomic positions and an optimized wave function for that particular geometry. Okay? All right. Now, so as I mentioned, Hartree Fock is like the baseline method for quantum chemistry. There are obviously significant limitations with Hartree Fock, right? So nowadays, almost if you go into the literature and you pull out a publication on some quantum chemistry calculations, it's rare that you see just a Hartree Fock calculation, okay? The reason is because all electron correlation other than exchange, which is the Pauli exclusion principle, is completely ignored, all right? Because I'm assuming a mean field approach with respect to other electrons. There are electron-electron correlation that I'm not accounting for, okay? So this is mainly the result of this, the Fock operators being one electron, okay? So as a convention, when you hear the term electron correlation or the correlation energy, whenever people refer to that, usually what they mean is basically what is the exact energy subtracting out the Hartree Fock calculation energy. Okay, so by definition, we usually treat the Hartree Fock as the exchange energy, and anything else that is not covered under your exchange, we call it electron correlation. Okay. The other limitation of the Hartree Fock approach is that there is this 4 index integrals. If you look at this part over here, this four index integral basically you have to account for the interactions between each electron with every other electron. Okay, so these 4 index integrals actually lead to n to the power 4 scaling with respect to basis set size. Okay, what this simply means is that as your basis set increases, your calculation costs do not simply increase in a linear manner, but rather increase significantly based on in accordance to n to the power 4 law. Okay, so obviously there are ways to there are some algorithmic tricks that you can use to lower this scaling factor, but formally it is a n to the power 4 scaling, right? All right, now. Even though, like as I mentioned, the Hartree Fock approach is the most basic method that you can use for quantum chemistry, it is still useful to go through some of the practical aspects of Hartree Fock calculations. Because when I talk about all these practical aspects of Hartree Fock calculations, what you will see is that they apply to the more advanced methods that I'm going to cover after Hartree Fock. Okay, so it is useful to think about Hartree Fock. There are 5 key components that you need to take into account when you are doing any sort of quantum chemistry calculations. Okay, so the first thing is what's your choice of basis set, right? So how do you choose a basis set in which to construct your gas wave functions, right? Somewhat related to the basis set is the effective core potentials. I'm going to talk about what they are. You also have to think about whether your calculations are just closed shell calculations or do they involve open shell systems. Okay, and of course all this affects the performance of your calculations in terms of things like how expensive it is to go to do your calculations, as well as the accuracy of the final result that you get. Okay, so these are the 5 components. So let me start with the first one, okay, which is basis set, right? So the basis set essentially is just the set of mathematical functions that you use to construct the wave function. Okay, so in the linear combination of atomic orbitals approach, that mathematical function is just your atomic orbitals, but by and large you usually do not just use your atomic orbitals, right? So in theory, when we talk about the Hartree Fock limit, we are talking about that the answer that you get for your wave function when you have an infinite basis set. All right. So in other words, if you have a basis set that's infinitely infinite in other words, you are not truncating the basis set. Okay. In practice, what you, of course, no, we cannot use an infinite basis set. Quite obviously, we need a finite set of basis functions to do our numerical solutions. So in practice, what people have done is to try to find finite basis set that allows you to approach the Hartree Fock limit as efficiently as possible. So the ideal is, of course, you want to use the smallest possible basis set and the least computationally expensive basis set to get to the Hartree Fock limit. Okay. All right. So one of the most common basis set that people use are the Gaussian functions. Okay. So we use contracted Gaussian functions. So for Slater type orbitals are basically functions with a e to the power negative r radial decay. Okay, so if you actually solve your hydrogenic Schrodinger equation, in other words, if you solve for your atomic orbitals, you usually encounter this e to the power negative r term inside your solutions. Okay, now the problem with the e to the power negative r term is that it cannot be analytically integrated. Okay, so so more commonly, instead of using those atomic type basis functions, the solution is to just use a linear combination of Gaussian type orbitals with e to the power negative r square radial decay to approximate those Slater type orbitals. Okay, so a typical approach, for example, the smallest possible basis set that you, one of the smallest possible basis set that you encounter in a lot of the quantum chemistry code is called STO3G. Okay, STO3G basically just simply means Slater type orbitals that are approximated by 3 Gaussian type orbitals. Okay, it is also known as a single zeta or a minimal basis set, right? And essentially what this means is that I'm going to approximate each of my Slater type orbitals with 3 Gaussian type orbitals with the form of e to the power negative r squared. Okay. And the advantage of the Gaussian type orbitals is, of course, that they are numerically more efficient and they can be analytically integrated. Okay? All right. Now, usually you can't just use the STO3G, so it is very rare that you just use the STO3G basis set for your numerical simulations. Okay? More often than not, you will actually have to go to multiple zeta or even split valence type orbitals. Okay. Now, multiple zeta just simply means that you are increasing the number of basis functions per atomic orbital. Okay. So some examples, when you actually get to your lab number 1, you are going to encounter all these terms over here, right? So there's this set of multiple zeta orbitals called CC-P CVDZ. I know this is a mouthful. CC just stands for correlation consistent. P stands for polarized. CVD just means CV means core and valence, and D or T just stands for double zeta or triple zeta. Okay, so essentially, you can just think of them that instead of just using 3 Gaussian type orbitals for my for each of my atomic orbital, I'm going to use more. I'm going to just keep adding more basis functions per atomic orbital. Okay. Now, another set of very popular basis sets are what are known as the split-valence or valence multiple zeta basis functions. Okay. In this type of split valence or valence multiple zeta functions, basically you still represent the core orbitals using just a single contracted basis functions. but your valence orbitals are now split into many functions. So in other words, you actually increase the basis set size for your valence orbitals, but you still represent your core orbitals using a single basis function. Okay, so those set of basis functions have this notation. For example, 3-21G, 6-31G. Basically, the numbers represent, for example, the number of primitives in the core, and for example, and the other numbers represent the number of primitives that are used in the valence orbitals. Okay. Now, why do you actually think that we will want to increase the number of functions in the valence rather than the core? Anyone? Yeah?
Yes, those are the atoms and the electrons that will bond.
Correct. Okay, so the reason why we do this is, of course, the core electrons usually don't participate very much in chemical bonding, right? So most of the chemical bonding actually comes from your valence electrons. So we want to increase the flexibility of your basis set with respect to the valence electrons so that we can describe those bonding changes better. Okay? All right. Now, so this is going to be a theme that we are going to come back to over and over again whenever we talk about basis function choice. Okay? The basis set choice is always a trade-off between how cheap it is to do the calculation and how accurate we want the eventual answer to be. Okay? So, of course, the larger the basis set, the more accurate the answer, right? But, of course, as you increase the basis set size, you also increase the cost of your calculation. So, tricks like this are one of the reasons why it can be, for us to actually get more accurate answers with less computational costs, right? There's nothing preventing us from doing the core electrons with many basis functions as well. It's just not efficient to do so, okay? So this is why we have something like the split valence basis sets, okay? All right, with the basis sets, you can also have options of adding polarization and diffuse functions. Now, this is actually very, very important, okay? Polarization functions are basically functions that you add to your atomic orbitals to give it even more flexibility, right? So very often your molecular orbitals require more flexibility than just what your atomic orbitals can give, right? So for example, ammonia, right, which is a very important molecule, right? If you just use a basis set without polarization function, what happens is that the equilibrium structure that you get is just a planar molecule. Okay, in other words, your nitrogen and hydrogen all sits in one single flat plane. All right, and if you actually know the structure of ammonia, you know that ammonia is actually not the structure of ammonia is not like that. The structure of ammonia is actually it looks like a tetrahedral, right? So you basically have a nitrogen in a different plane from your 3 hydrogen atoms, okay? So the way that you usually do this is to just add basis function of one quantum number of higher angular momentum compared to the valence, right? So in other words, what this means is that if I'm using the first for the first row of elements, what I would do is that I'm going to add d orbitals to my first row, and so on and so forth. Okay, so the notation is something like what is 6-31G star, or 6. This is the old notation. More often, you actually now see the new notation, which is like 6-31GD or 6-31 bracket 2dp. 2dp just simply means that I'm going to add 2d functions for my heavy atoms, and I'm going to add an additional p for my hydrogen atoms. Okay, so this essentially is further increasing your basis set size for and basis set flexibility such that you can get more accurate answers. Okay. Now, I want you to make note of this because in lab number 1, you are going to do this calculation. Okay, you are going to do the calculation of ammonia with and without base polarization functions, and you are going to look at what's the final result that you get for your ammonia molecule. Okay, so this is polarization functions are extremely important. Okay, now the second type of basis set expansion that you can use is what are known as diffuse functions. Okay, these have a certain use. Okay, when you have anions, especially those with very diffuse, diffuse electron clouds. Okay, typically your normal basis functions, even when you add on polarization functions, they do not have sufficient spatial extent to actually model diffuse electron clouds. Okay, so what the diffuse functions do is that essentially they add additional basis function that has a greater extent in real space, such that you can actually model those electron clouds more accurately. All right, so this is particularly important when you are simulating things like anions with a negative charge, and those actually tend to have excited states with more diffuse electrons clouds. Okay, now the notation is this plus sign over here. Okay, so you look, if you compare the basis function that we have here with the polarization function, you see that the main difference is whether there's more plus signs or so if you have the more plus signs you have, the more diffuse functions that you have. Okay, and for your correlation consistent basis sets, there's this AUG, which just means augmented basis set, which means the inclusion of diffuse functions. Okay, all right. So basis set choice is definitely one of the most important considerations you have to make when you are doing quantum chemistry calculations. All right, so it's not unique to the Hartree Fock approach. All right, so if you are doing any sort of quantum chemistry calculations, even with with some of the more correlated methods, this again, the basis set choice is one of the most important decisions you have to make. Right. Sometimes it is practical. You just have to use a smaller basis set because your the calculation is so expensive that you cannot afford to use a bigger basis set. But when you do so, you have to keep in mind that your answers are probably not going to be as accurate as you want them to be. Okay? All right. Related to the issue of basis set are what are called effective Core potentials. Effective Core potentials is a very simple concept, right? So when we think about heavy atoms, in other words, anything other than the first 2 rows of your periodic table, they have many, many electrons. And so it is intractable for me to treat all the electrons for the heavy atoms, right? So the way that the trick that we use to handle heavy atoms is basically to treat the core electrons, which is basically most of the electrons, as part of an effective core. In other words, instead of thinking of something like iron with its many, many electrons, I'm going to basically treat iron as basically an effective core with all the up to the p electrons, and I'm only going to treat, for example, the valence electrons as actual electrons in my calculations. Okay, so the effective core potentials essentially replace those core electrons together with the nuclei core as basically using some analytical function that actually represent the combined interactions of that core with the electrons. Okay, so one of the key selection decisions that you always have to make is how many electrons do you want to include in the core itself, right? So if you only think that the outermost orbitals are participating in the reaction and that's all that you're interested in, of course you can choose effectively core potential that has more core, electrons being considered in the core, but you may also sometimes want to include some of the outer orbitals inside the non-core part as well, so that you can model certain types of hybridization and interactions more accurately. Okay? All right, so you don't really have to worry about this for your lab number 1. For lab number 1, we are dealing with just first 2 rows of the periodic table. For our quantum chemistry part, we are not worried about effective core potentials at all. Okay? All right. So the third thing that we need to take into account when we do quantum chemistry calculations are whether to do an open shell or a closed shell calculations. Okay? So for closed shell systems, in other words, systems where all your electrons are in pairs, okay, up and down pairs. So an example is your hydrogen molecule. You basically have 2 electrons in the molecular orbital, and your electrons are paired up in the low energy state with electrons with opposite spin. Okay, so those are called closed shell systems. Okay, and for those, you will do what is called the restricted Hartree Fock approach. Okay, where you essentially treat all the shells as basically closed. Okay. Now, what happens if you have unpaired electrons, right? So when you have unpaired electrons, you will need to deal with each electron separately. Okay, so there is what is known as the restricted open shell Hartree Fock approach. All right, so or ROHF. It is very similar to the restricted Hartree Fock approach. The only difference is that the density matrix for the singly occupied orbitals, you are no longer multiplying them by 2, right? Because you no longer have a pair of electrons, right? The advantage of the restricted open shell Hartree Fock approach is that the wave functions are still eigenfunctions of the S2 operator, okay? But it does not account for spin polarization in the doubly occupied orbitals, okay? So, so more typically, if you actually have unpaired electrons, you do what is known as the unrestricted Hartree Fock approach, okay, or UHF. In this case, you don't actually pair up your electrons. You treat each electron, the spin up and spin down, separately. The unrestricted Hartree Fock approach, by definition, it will include the effect of spin polarization, okay? So, however, the wave functions are not eigenfunctions of the S2 square operator. So, this means that sometimes you can have spin contamination, and that may actually affect the accuracy of your calculations. Okay, so typically you will whatever quantum chemistry code that you use typically will report whether you have significant issues with spin contamination. Okay. All right. So we now come to the last 2 considerations of the Hartree Fock of quantum chemistry calculations. So here I'm going to talk about the accuracy and performance for just the Hartree Fock approach, and we are going to come back to these two considerations over and over again when we talk about the methods that are beyond the Hartree Fock method. Okay, so the first thing is accuracy, right? So in general, Hartree Fock gives you extremely bad energies. Okay, so the only reason why we start from the Hartree Fock approach is really because of its conceptual simplicity, right? I can explain to you how that whole electron correlation and circular determinant works without in an analytical fashion, but in most cases, electron correlation, which is everything that is outside of your exchange interaction, is actually very, very important in chemical bonding. Okay, so what this simply means is that there's a huge chunk of correlation energy that you are not taking into account. So your predicted energies from your Hartree Fock calculations are usually quite bad. Okay. The one exception is protonation energies. Okay, protonation energies are usually okay. The protonation energy is simply the energy of putting a H plus into your system, right? And that is actually okay because, well, you don't have any electrons in H plus anyway, right? So, so your electron correlation is not as big a factor when we talk about protonation energies, right? There is something called Koopman's theorem, which states that basically the first ionization energy is equal to the negative of the orbital energy of your highest occupied molecular orbital. Okay, so that actually gives you your ionization energy from your Hartree Fock calculation. Now, despite the fact that your energetics are actually not that great, the geometry is reasonable, right? So this is actually somewhat paradoxical, but it's actually interesting. So what this simply means is that even if I don't want to use my Hartree Fock for my final energy calculation, I can actually use the Hartree Fock approach to actually get a reasonable geometry for my molecules first. Okay, so typically the ground state structures are actually usually quite good. But transition states, for example, when we think about the transition state of reactions or transition states in diffusion, those can be very problematic, okay? Because whenever we think about transition states, we usually have partial bonding in the transition state, okay? So, and Hartree Fock, because it doesn't account for electron correlation, those partial bonding tends to be not very well described, okay? All right. So in terms of performance, formally, Hartree Fock is n to the power 4 scaling, as I mentioned. In reality, it is there can be significant speed-ups of Hartree Fock calculations through things like using symmetry. Okay, so for instance, if you have a very highly symmetric molecule, you can use symmetry to minimize the number of calculations that you do. Okay, you can also use some tricks, numerical tricks like estimating upper bounds for your 4-index integrals, which is what is actually contributing to that n to the power 4 scaling. And you can also use some fast multiple and linear exchange integral computations to speed up your calculations. Okay, so for practical geometry optimizations, it is very often helpful to first compute your geometry using a smaller basis set to actually get an initial geometry, and also to get a guess for your Hessian matrix before you then actually do a more accurate calculation using a larger basis set. Okay, so this is a trick that is used very often, regardless of whether we are using the Hartree Fock approach or not. Okay, so if you are starting with some molecule, or rather it is not a very well-known molecule, and you are not 100% sure about your initial guess geometry, you can actually use some very small basis set to try to first quickly relax your atoms to some reasonable initial starting structure before you then redo your calculations using a larger basis set. Okay? All right.